constant. Well, what did that intros do? So at the beginning, m was not a constant. It was universally quantified. What intros does is it says, pick an arbitrary n and m. So after we've done the intros, now in the hypotheses we have a particular n and m. We don't know what they are, they're arbitrary, but they're particular things. Now we're reasoning by induction on m, which sort of re-abstracts it, but m stays concrete. And that's what gets us to this mangled state. So what do we need to do? We need to make sure that the induction hypothesis has m under a quantifier. And how do we do that? Well,
maybe we can do induction on m before.
We could do induction on m. That could work instead of m.
Induction on n before.
Oh, I see. We could do induction on n before the intros. Aha. Will that work? Let's try. Did it work? Yes. Surprises me. Why did that work? I thought it was going to not work.
Induction got smarter.
Maybe induction got smarter. Okay. Okay, so induction got smarter in what coq version? 8.6 maybe? Okay. Before 8.6, this would not have worked. Now it does work. All right, so my example doesn't work, and I need to go back and fix it. But induction is probably not always smart enough. So what could we do instead? Well, we could do a couple of things. We could do induction on m, since the whole thing is symmetric. We could do induction on m. Or we could change the statement of the theorem to swap n and m. Is that true? Well, in any case, or here is the right way to do it, is to use oh, sorry, no. Sorry, I'm confusing myself. If we just, yeah, sorry.
This is essentially what induction now does.
All right, I apologize for the confusion. I think if we just rewind and observe that n is the first thing bound, so if we don't do the intros, I think this is even true before 8.6. If we don't do the intros, then induction will say, okay, grab that first n and do induction on it. N will remain quantified, and that's exactly what we need. Okay, if n and m had been introduced in the other order, then we would have a problem. And then we would need either the new smart induction tactic or, and do I have it here? Yes. We can use a thing called, oh dear, we're almost out of time. We are out of time. So let me not try to get coq to accept it. I will just go back here and show you this, which is this generalized dependent, which says, so we've done the intros. Both n and m are in the context. Generalized dependent says take something that's in the context and move it back into the goal with a quantifier. So this is the way of controlling the form of the induction hypothesis when we get into a state where the variables are too concrete. Okay. Good. One last thing. Another thing that can happen sometimes that can get a proof stuck is that a definition needs to be unfolded. Coq is already a little bit smart about unfolding definitions, so it will automatically do a bit of unfolding, but it doesn't do very much unfolding. In particular, in this situation, so here's a definition, bar of x, match x with blah, blah. And now, if we try to simplify some equation involving bar, if we try to simplify some use of bar, bar always returns 5. So if we did kind of fully simplify out everything, we would see that this is just an obvious reflexivity. But simple will not do it. Why? Well, simple is a little bit conservative about how much it expands. And the reason is that simple is trying to strike a balance between computing enough to expose things that are useful for making progress in a proof, but not exposing everything. Because often, we've been dealing with fairly small definitions here, but if the definitions get big, if you compute out everything and reduce it to a totally finished normal form, it will typically be huge. And then those are hard to reason about. So you don't want to unfold everything. You just want to unfold a little bit at the outside, and simple is basically a heuristic that says if doing a little bit of unfolding will cause further computation to happen. So if unfolding an application, if unfolding the left-hand side of an application will enable some further computation, then simple will do that unfolding, and otherwise it won't. In situations where simple isn't doing enough unfolding for you, you can do it manually by saying unfold. So here we are unfolding bar manually to make progress. Okay, now let's see, a couple more things here. I'm going to leave you to read for yourself this last bit. No, let me just say it really quickly. So destruct can be used. So destruct, remember, takes an equality and examines how it came to be, and gives you a that's inversion. Destruct takes an element of an inductively defined type and gives you a case analysis. An element of an inductively defined type could be a single variable, or it could be a compound expression that just happens to return a number or a color or whatever. Destruct will work with both, but destruct throws away the expression that you destructed, and sometimes that will leave you in a stuck state. So let's see. Here is an example where it does work, and here is an example where it doesn't work. And the reason is that at some point in the proof, you need to know that you need to know that the thing you destructed on, the expression you destructed, is equal to true or equal to false, and you don't have that equality. So how can you get that equality? By saying destruct, and then there's a little optional bit that's EQN colon, and you can give a name. So this EQN colon stuff gives you a hypothesis with the equality that you would be missing otherwise. Okay, I know that's fast, but just to give you a preview of what you can read in the chapter. And then one last thing, which I will say very quickly. Mindless proof hacking is a lot of fun in coq. You can get a long distance in coq without thinking at all. And it's actually a pretty useful strategy. So it is a terrible temptation, and you shouldn't always resist. But if after 5 minutes you realize that you're going in circles, or you haven't made progress, or you have absolutely no idea what's going on, then you should step back and try to think. So the typical mode is a typical coq user sitting at their keyboard does not have their brain engaged all the time. They're just pattern matching, applying tactics, blah, blah, blah. But at some point, something unexpected happens or they get stuck and they say, oh, I have to re-engage brain. And then you have to actually look and see, okay, what is this really saying? Does the conclusion follow from the hypotheses? Is something mangled? So you need to develop the skill of realizing when you need to re-engage your brain and how to look at the state and figure out how you got into a mangled state or if the state is mangled. One really useful way is to go back to good old pencil and paper. So my recommendation for you is set yourself a time limit. 5 minutes is a good amount. If you've been proceeding without thinking and don't seem to be making progress for 5 minutes, then stop. Actually set your laptop aside, take out a piece of paper, and attempt to prove the thing that you're trying to do with coq informally in the usual way that you've been used to on paper. And that will almost always teach you how to go back and do it the formal way. Okay, and with that, it's time for lunch. And we start in the afternoon at?
So after the lunch, there's this homework session where I can exactly practice that skill.
Okay, so we can practice hacking and thinking.
Instead of seeing TAs, first try to use the pencil and paper. And then there's coffee break again at 3, and the last session is at 3:30.
Okay, so the homework session starts officially at what time?
Right after lunch.
Right after lunch. Whenever you're finished with lunch, come back here, work on problems, and you've already seen, but there are optional problems and ordinary problems and advanced problems. The ordinary try to do all of the ordinary problems. If those seem easy, then try to do some advanced problems. But try to get through those 2 chapters so that you are up to speed when Ben begins at the end of the afternoon.